The Earth's atmosphere, once an empty and unknown place, is rapidly being explored by the high-flying robots of the space age. To learn the secrets of this vast region, men launch instrumented rockets into the sky and compile valuable data from the information relayed back. Since the Navy has an ever-increasing need for more knowledge about the atmosphere, Navy scientists have long sought to develop more effective rocket probes to aid in their investigations. In December of 1959, the laboratory department at the Naval Missile Center was presented with a specific task: develop a probe with certain well-defined capabilities. A paper presented at a 1957 meeting of the American Rocket Society proposed a vehicle composed of two Sparrow motors mounted in tandem, and predicted that by launching this configuration from an aircraft, altitudes greater than those required could be achieved. The feasibility of this proposed system was carefully checked, involving studies of aerodynamics, weight and balance, trajectory analysis, launch phase, and preliminary design. The studies were encouraging. A number of Sparrow motors and launch aircraft were available, and it was this combination of factors that led to the detailed design and development of SparoAir. Since aerodynamic heating during flight can create stagnation temperatures up to 1900 degrees Fahrenheit, the material used for the SparoAir nose cone had to be highly heat resistant. To comply with this requirement, NMC engineers designed a cone of laminated construction. First, phenolic asbestos tape was wound on an aluminum mandrel. Next, the basic form was covered with a tightly wound layer of fiberglass tape. After which the entire assembly was placed in an oven for curing. Finally, the cured nose cone was placed in a profile lathe and machined to exact specifications in preparation for the finish coats of resin. The telemetry package, which had previously been submitted to a full range of acceleration and shock tests, was then installed in the completed nose cone. Because atmospheric pressure had to be maintained throughout the entire flight, it was necessary to seal the holes when inserting the holding screws. The assembly was complete when the instrumented nose cone was mated to the forward motor section and turned into place, and the tunnels containing the electrical leads from the nose section to the timer and umbilical plug were attached. But even as SparoAir 1 was being readied for launch, the designers were studying ways and means to improve it. A fundamental change would be the use of current air-safe motors, which would allow the rocket to be fired from a rail-type launcher instead of the ejection type used here, greatly simplifying the operation as well as some of the components, and making the new version more reliable and less costly. One of the modifications introduced in SparoAir 2 was this durable and considerably less expensive nose cone of stainless steel. As in the earlier model, many of the supplemental fittings were manufactured in the shops at Point Mugu, where, because of the critical nature of these components, a flawless product was a prime consideration. Here in the metallurgy laboratory, a nose cone adapter ring is set up for an X-ray picture. The photo equipment, which is about 5 times more powerful than the average medical X-ray, is capable of detecting a variety of imperfections in the metal castings. Flaws in the metal resulting from cracks, areas of high porosity, and so forth, show up as variations in the shadow pattern on the plate. Assembly of the SparoAir 2 vehicle was very similar to that of its predecessor. The difference lay in the modifications made to the component parts. The second stage fins were increased in size by 1/3 for improved aerodynamic stability. The exhaust nozzle of the second stage is a standard Sparo component. But in SparoAir, it is given an additional task. When the second stage ignites, stagnation pressure from the exhaust causes a special slotted and threaded disc to deform, and separation occurs. No changes were made in the separation disc and center coupling, but the stage timing system was greatly simplified. The timer itself was placed in the payload section, and the igniter, here being installed, was modified to provide more reliable ignition at high altitudes. In the missile field, simplicity is economy, and final assembly of the 2 stages of SparoAir was a remarkably uncomplicated process. Some of the major changes in SparoAir 2 were incorporated into the nose cone assembly. A vital unit was the payload battery, which was given the additional task of supplying power through capacitors for second stage ignition. Again, to assure the maintenance of atmospheric pressure, the instrumentation package was thoroughly sealed before being placed in the adapter ring, which also contained the timer, the umbilical plug, and the timer lanyard switches. The assembled unit was first tested for accuracy of operation. And then inserted into the nose cone. A further improvement was the placing of the telemetry antennas on the nose cone, thus eliminating the cumbersome wiring tunnels. With the positioning of the umbilical plug, the unit was ready for final enclosure. The ease of assembly that characterizes SparoAir is further demonstrated by this last step in the sequence. The launch aircraft selected for SparoAir was the Navy's F-4D Skyray jet fighter. Ready for launch, SparoAir has a basic body diameter of 8 inches, an overall length of 145 inches, and weighs slightly over 300 pounds. The launcher used was the Aero 4A, regularly employed in the Sparo 3 system. In operation, the first stage is initiated by the aircraft, and the first motion of the vehicle on the launcher closes the lanyard switches that initiate the second stage timer delay train. At an altitude of about 26,000 feet, the pilot is ready to begin the launch maneuver. Hurling the aircraft into an 89-degree angle of climb, he releases the rocket, using the over-the-shoulder bombing technique. With its 40-pound payload, SparoAir 2 takes off for the outer reaches of the Earth's atmosphere. It will attain a peak altitude of some 65 miles. A new model is already on the drawing boards, with improvements that will send it 200 miles into space. And it is reassuring to know that Navy ingenuity will keep the cost of SparoAir 3 considerably below that of any other similar probe.